In class, we talked about how matter on large scales is electrically neutral, so we don't really get a good sense for how much charge we're encountering every day. So let's go through the calculation of an example that we just kind of said what the answer was to. So suppose I have an aluminum ruler that has a mass of 500 grams, and what I'd like to know is if I could separate off all the electrons in that ruler, how much negative charge would I have in my hand? So you can do that problem in a number of ways, just like any problem that we do in class. There are a multitude of ways to do it. The way I'm going to do it is I'm going to think about the ruler and count how many aluminum atoms are in the ruler and then how many electrons are in each one of those aluminum atoms. So you could go through that in a number of ways. You could remember your chemistry and look up Avogadro's number and go through all those things. But I'm going to start quite simply with the mass of a single aluminum atom, which if you go look it up, it's 4.4789 times 10 to the minus 26 kilograms. And the mass of my ruler is 500 grams, which I'll write as 0.5 kilograms. For each one of those aluminum atoms, they have 13 protons. That's what makes it an aluminum atom. And if it's neutral, which by and large the ruler is, then for each proton there's also a neutron. So for every aluminum atom, I'm going to say that the number of electrons is 13 electrons per atom. Okay? And then to get to the charge, we'll need to know what the charge on the electron is. So the charge on the electron is the fundamental charge. It's the negative value of the fundamental charge, which is minus 1.60 times 10 to the minus 19 coulombs. Okay, so we're interested in the total charge, and by and large you can calculate that by looking up numbers and just multiplying them together. And what that boils down to is something that we're familiar with, that we do all the time in physics, which is dimensional analysis, multiplying a whole set of numbers together such that the units that the numbers carry cancel each other out, and in the end give us the thing that we care about, which is total charge. So I'm going to write this out as a long string of numbers that just have to be multiplied together, and we'll get to our answer. So what we're interested in is the total charge, which I'll write as Q tot. Okay. Now, dimensional analysis can be done in one huge string, or it can be done in parts where you slowly expand the parts. So I'm going to do it that second way because I can't just off the top of my head imagine what all the little numbers I need to multiply are together. Okay, so what I know is that the total charge is going to be something like the charge carried by a single electron, which we wrote as little q up there, times the total number of electrons in the problem. Okay, so I know little q, that's written up there, so now I just need to expand what the total number of electrons in the problem is. Okay, so I have q, and now I'm going to expand the total number of electrons. That's going to be the total number of aluminum atoms in the problem, or the total number of aluminum atoms in the ruler, which we'll figure out in a moment, times the number of electrons in a single aluminum atom. Okay, so you can see how this is going already. I know Q and I know Ne, so now I need to expand this N, which is the total number of aluminum atoms in the problem. Okay, so the way I'm going to approximate that is, let me regroup this a little bit, so I'll put Q times the total number of electrons per aluminum atom. So this number of aluminum atoms I can figure out from the masses in the problem. It is given simply by the mass of the ruler divided by the mass of a single aluminum atom, both of which are numbers that I know up here. Okay, so you can do this problem in a variety of ways. I've bypassed using Avogadro's number and all those things you learned about in chemistry class by simply using this mass ratio. You can go and do it that way if that's the way you remember it from chemistry class, and what you should find is you'll get exactly the same answer as we get here. It doesn't matter which way you do it, there's always more than one way to solve the problem. Okay? In fact, it's useful to have more than one way to solve a problem because you can check an answer and make sure that you got it right if you have any uncertainty in the way you did the calculation. Okay, so at this point I know all these numbers, so I can put them in. The charge on the electron is minus 1.60 times 10 to the minus 19 coulombs. There are 13 electrons per atom. Okay, and this coulombs here is actually coulombs per electron, if I wanted to be completely explicit here with my units. Okay, and then here I have the mass ratio of the masses involved. So the mass of the ruler is 0.50 kilograms. Just as we've been doing all along through physics, I always convert everything into pure SI units. So we were given the mass of the ruler in grams, but I know I want everything to cancel out and be consistent with constants I use. So that's why up here I converted to SI units. And then the mass of a single aluminum atom is 4.4789 times 10 to the minus 26 kilograms per atom. Okay, now I like to be completely transparent and blatant and diligent about everything. So what you'll see here is that indeed all my units cancel and give me what I expected. This electron cancels with this electron. This kilogram cancels with this kilogram. This atom cancels with that atom. And what you'll see is that I have a whole bunch of numbers left, and indeed I'm left with the unit I care about, which is coulombs. Okay, so if I punch that into my calculator, okay, you'll need a scientific calculator to get through the course, then that all comes out to be minus 2.32 times 10 to the 7 coulombs, which in ordinary number is minus 23 million coulombs, which is, as we said in class, a lot of charge. You'll recall that we said a typical lightning bolt has maybe 10 coulombs of charge, and this is millions of times larger. So ordinary matter is electrically neutral, and despite having large amounts of charge within it. Okay, so we'll do another problem again sometime. Good luck.